Hi everyone, this is Christoph here. We couldn't cover all the slides in yesterday's seminar, so I wanted to cover the ones that we didn't cover yesterday through this little video here. And basically yesterday's seminar was very much about systems thinking or systems in general, and we discovered that there's different types of problems in the environment, and some are simple, some are more complicated, and some are complex, and we even talked about wicked problems and super wicked problems. And we also discovered that, in terms of addressing these problems, we need a different way of thinking. And that conventional thinking is sometimes not the right way to actually address these wicked, systemic, and complex problems. So we then started talking about systems thinking. And what I would like to take you through now is an analytical tool or a method that can help you with systems thinking. And that tool, that analytical tool basically, is called systems mapping. So before we start talking about systems mapping, I actually wanted to ask you, and this is probably a very one-sided conversation right here, but I actually wanted to ask you and think about what a map really is. And if we start thinking about a map in general, a map is always a simplified version of reality. It's always a very good attempt, but it's never a really full representation of reality. But maps have certain functions, or they are supposed to do something for us. And what they're supposed to do is to help us get a better picture of reality. And not a very accurate one or 100% accurate one, but helpful in a certain way. They also help us to orientate when we are a little bit lost, and to find some meaningful way through that disorientation. And in the case of the system map, they help us to understand where we need to intervene. So systems mapping is useful for a few reasons. They help us to understand the whole better. They help us to understand that a system is more than just the sum of its parts, but that these parts are interconnected, and that through this interconnection something emerges that is what we're interested in, or that is what we want to take apart. So systems mapping helps us to understand how these different interactions between elements of a system can also lead to certain outcomes. And I guess in the context of sustainability, it's sometimes outcomes that we are not aspire to, or outcomes that we want to change. If we think about changing them, systems mapping also helps us to move away from linear types of thinking, where we think that if we just intervene by doing A, automatically B will happen. And by sort of getting that more holistic, more fine-grained understanding of how we can intervene or how we can change, it helps us to improve the strategies that we come up with if we want to change the system or a specific outcome of a system. I wanted to show you a really cool systems map, which is an obesity map. I'll try and bring this up here. Yeah, so basically what this is, and I hope you can see that, guys, but this is someone's incredibly attempt to map the system of obesity, or to map the problem of obesity and all the different elements and factors that contribute to it. And it's really messy. It's a really complicated representation of a complex problem, I guess. But what you can see here, without going into too much detail, is you can see lots and lots of different elements. Elements are these boxes, and then you can see all these different connecting arrows. And basically what that means is that no element just exists by itself, but that all elements are connected with each other and that they interact with each other. And in fact, these elements come from or represent different backgrounds. So you've got the physiology here in blue, which is that circle down here, relating to some really basic elements such as energy balance, so really basic physiological elements. But then it's also about psychology, individual psychology, but even social psychology is in here. So you can see how all these different domains in our environment, from the biophysical, physiological, to the very social are actually all intertwined and all relate directly or indirectly um, to a certain degree to that problem of obesity. And really, that shows that none of these elements, contribute to obesity by itself, but that they're all interconnected and they all co-contribute to that problem. It also shows that all elements influence at least one other element. So that means there's constant interaction between all these different elements in the map. And again, this is not a perfect representation of the obesity problem, but it does give us some sort of orientation, and it helps us to understand that problem of obesity more holistically. So I guess if you're interested in tackling obesity in Australia, drawing up such a systems map could be a really good starting point, to maybe find a solution or to maybe craft something that is a meaningful intervention strategy. And I say maybe because we never know, as we've learned, complex systems are unpredictable, they're very uncertain, and surprise is always an element of them. You can never really know if what you're doing is actually having the intended effect. But with that systems map, you can at least get a step closer and make a more meaningful intervention strategy. So I just wanted to show this really cool example to you. But what are the basic elements then of a systems map? And you've just seen them in the obesity map, but this is sort of taking them apart and looking at them more closely. So the basic elements of a systems map is that we've got variables, and the variables are represented here in this picture with A and B. And variables or elements are nothing else than an element or a factor or a thing in that system that relates to or is important to that system's functioning and working and so on. You've got relationships between elements, so that's represented by the arrow here, the relationship from A to B, meaning that A has a certain influence on B. And we talked about this before. Relationships between elements is really key consideration in systems thinking. But that arrow alone doesn't necessarily tell us something about the quality of that influence. So in the arrow below, you've got a minus and a plus sign, and that really then tells you that A can have a positive influence on B, which is then a plus sign, or a negative influence on B, which is then represented by a minus sign. And there's another core element of systems mapping, and that's time delays. And that basically means that whatever you do, whatever A does not have an immediate influence on B, but there's a time delay related to that influence. But these are sort of the basic elements of how to draw a systems map. And when we go quickly back to the obesity map, you'll see that there's lots and lots of elements and there's lots and lots of relationships. And in that case, they are not specified with plus and minus, but there clearly must be some underlying understanding of if it is a positive, or down here at the bottom right, you can actually see, so the positive influence is a full line and the negative influence is a dotted line. So we've got all that covered in that map. So through these through these elements, the variables, the relationship, the influences, and the time delays, you can start mapping very basic system behavior and two sort of like core underlying elements of that basic system behavior are feedback loops. And there's reinforcing feedback loops and there's balancing feedback loops. And those two really make up the core of systems behavior. So we start with the reinforcing feedback loop. What's a reinforcing feedback loop? A reinforcing feedback loop basically tells you that if you if you have a condition or a performance here in the box and you do something, then this reinforces the condition. Okay, so an example would be, I've got some money in my bank, I get interest, which is the growing action. Because I get interest, I get more money in my bank, and then I get even more interest. So it becomes this self-reinforcing cycle. These cycles are also sometimes known as vicious cycles because they can actually have very negative impacts as well. And an example where these cycles can be really bad is the 2008 housing crisis that started in the USA, which then sparked the financial crisis. And that basically was driven by very unsafe mortgage lending, which increased housing prices, which then meant that more people were taking up unsafe mortgages to afford houses, which then drove up again housing prices and so on and so forth. So it created this really vicious cycle of constantly reinforcing unsafe mortgages, and increased housing prices until the bubble or the system got out of control and the bubble burst. On the right side, you can also see a very social element of that reinforcing cycle. You've got here that you've got A acts, which is the manager, and the manager makes decisions and directs the subordinates. And by doing so, the subordinates think that, well, he doesn't want our input anyways. Because of that, they're sort of leaning back and say, well, I'm not going to contribute anyways. And then the manager thinks that my subordinates don't care, and he's then more inclined even to make decisions on their behalf. So then this is a very social example of a self-reinforcing feedback loop in the system of an organization where the manager and his employees interact with each other. Mind you that these examples only show growing. Oh, sorry. This graph relates to that. Sorry, I should say that first. So this graph is actually a representation of what happens when you face a self-reinforcing feedback loop. So if you plot self-reinforcement in a graph, and the x-axis in this case is time, and the y-axis is quantity, you get these graphs of exponential growth. And they're actually quite important because we usually think in very linear ways, but once we're confronted with self-reinforcing feedback loops and systems where self-reinforcement is quite strong, we actually don't face linear growth anymore, but we face exponential growth. And a very prominent example is population growth. More and more people making more and more babies, which results in more and more people making more and more babies. And that's a classic example of exponential growth. But we also see that, for example, with greenhouse gas emissions and economic development, where over the last, 150 to 200 years, the emission of greenhouse gases was very much linked to economic growth. So as soon as the economy grew, we emitted more greenhouse gases, which then enabled the economy to grow even more, which then led to more and more emissions. So it's this constant reinforcing cycle, which then leads to exponential rather than linear growth patterns. We can also think about what does that mean for intervention strategies. If we don't think linear anymore, we have to think about how intervention strategies actually play out. If we intervene in a system, we might not be able to see anything for a long time because of that exponential growth path. But after enough time has passed, we might see a really effective and really prominent outcome of that initial intervention strategy. So we've got to keep that in mind as well if we think about intervention in complex systems that are governed by these feedback loops. But systems can also have um, another feedback loop, which is the balancing feedback loop, um, or the correcting or the dampening feedback loop. And basically, what it is that you have a condition or a performance, and because of that, you do something, and that something that you do takes a corrective action on that condition um, that you have. And a very easy example for that is if you're hungry, which would be the condition, then you eat, which is the corrective action. And once you've eaten, you're less hungry. So the condition has been balanced out or has been reduced. It's the same when you're hot. When you're hot, you sweat. It's another corrective action. Or when you need a rest, you sleep. So these are all sort of like balancing feedback loops. In this case, the system is you. Balancing feedback loops that correct or dampen something. And these balancing feedback loops are actually really important, and they're always there because they make sure that the system is actually working like it is supposed to work and to fulfill a certain function and not to go completely out of balance. And these correcting feedback loops also create the stability in a system. So sometimes when we want to intervene, it is these balancing feedback loops that actually prevent something from changing completely, because these balancing feedback loops maintain certain status of the system. And while these other feedback loops that we just talked about, the amplifying one or the reinforcing one, they're often quite easy to discern and quite visible. Sometimes these balancing feedback loops go a little bit unnoticed. If we plot a balancing feedback loop onto a graph, we usually get something like that. And you could see the graph goes up. So that could be, for example, you're getting more and more hungry, and once you reached that top tip, you start eating. So then your condition goes down, you're less hungry because you've eaten, and after a few hours, you're slowly getting more and more hungry again. So the curve goes up again. You reach another tipping point, or you reach another top point. You start eating again. The curve goes down. So basically, if you plot a balancing feedback loop against time and x in this case, in the y-axis, represented by the x in this case, it would be the level of hungriness. Then you would get this oscillating graph. And usually when balancing feedback loops are doing what they're supposed to do, these corrective processes, which are really important, usually go unnoticed. So when we eat enough food, or if we do get enough sleep, we take these processes pretty much for granted. But when a system is out of balance, they usually become very visible. So that means that these loops become more prominent when a system is not doing what it's supposed to do or what we desire it to do. So that also means that if we want to change a system towards more desired system behavior like sustainability, these feedback loops really prevent the system from moving quickly into a new direction and quickly into a different state where it might be more sustainable. But let's go back to these amplifying feedback loops again that we talked about before, the vicious cycles that we talked about. One example of a lot of different amplifying feedback loops coming together is around greenhouse gas emissions in the atmosphere and its effect on global temperatures. And if you just look at the right side of that diagram, so what you see here in total is greenhouse gases in the atmosphere is in the box, which is sort of that variable that we are interested in looking at. And then you see lots and lots of different self-reinforcing feedback loops that all contribute to greenhouse gases in the atmosphere. And what we see on the right side, for example, is a really interesting feedback loop that I want to explore with you a little bit further. It's termed here albedo on the right side with a little r at the top. And the albedo reinforcing cycle basically says that if greenhouse gas emissions are really high in the atmosphere, that affects global temperature, obviously. And global temperatures create or lead to the melting of polar ice. And what that means is that the ice caps at the poles are being reduced, so there's less ice at the poles, and that white surface at the poles actually has a reflecting purpose. So it reflects the sun radiation that comes back into the universe. So the reflectivity of the Earth is getting less because the ice is melting, because there's less white area, so there's less reflection of sun rays back into the universe. That means that there's more solar heat being absorbed. So because there's less ice, there's less white, there's less reflection, there's more solar energy that can actually be taken on, and that leads to the increase of global temperature. And becomes this self-reinforcing cycle that we can't even do anything about anymore. Once we've reached that tipping point where global temperatures lead to polar ices melting, leads to even less reflexivity, leads to even more absorption, you create this vicious cycle of constantly reinforcing elements. And another important or interesting part of this is if we stay with that cycle but look down, there's the methane cycle. And it's closely related to that albedo cycle. So if we look at, on the right, ice at poles, the logic goes that global temperatures increase lead to less ice at the poles, and that then, in the methane cycle, means that the permafrost is being exposed. And the permafrost is a type of soil that is kind of semi-frozen. And it actually contains quite a lot of, or underneath it, it contains a lot of methane gas. And methane gas is a greenhouse gas, but a really active greenhouse gas. So if we lose the ice at the poles, it means that the permafrost is being exposed, which then leads to the release of methane, which is stored underneath that permafrost. And these greenhouse gases, methane in that case, highly active greenhouse gas, leads to even more of these greenhouse gases in the atmosphere, which leads to higher global temperatures and then kicks in again, reinforcing that albedo cycle. So you can also see how the different cycles are interlinked and relate to each other, really creating some really vicious self-reinforcing cycles that become incredibly difficult to stop once a certain tipping point has been reached. And this is really it. These were all the slides that we wanted to cover in the lecture but couldn't. Please use this analytical tool to make sense of certain systems. If you want to use it in your case study, relating transport or whatever case context it is that you've chosen, think about the different variables that you can map, think about their influence, and if you do that, also justify why you've done that. If you choose to do that for your assignment, justify why you've done that. And it could be a really interesting tool to make sense of quite a complex topic and to understand it in a bit more detail and to think about coming up with some more meaningful intervention strategies.